folks, welcome to your second set of Chemistry 1 video notes. Today we're going to talk about how chemists express their data and the steps to converting between different types of units. By the end of this lesson, you should be able to define imperial and SI units for time, length, mass, volume, and temperature, use dimensional analysis to convert between units, and report your answers to the correct number of significant figures using scientific notation when appropriate. You should also be able to define accuracy and precision, and express the accuracy and precision of a set of data using percent error and standard deviation. Let's get started. First off, you're probably wondering what a unit even is. Think of a time when you've measured something, maybe in elementary school when you practiced reading a ruler. You might have measured the diameter of a quarter and learned that it is 0.75 inches wide. This measurement, like all measurements, includes a number, 0.75, and a unit, inches. Units help us understand what a number in a measurement means. Units are nothing more than specific systems for counting things, like how many inches wide a quarter is, or how much space a quarter takes up, or how much mass a quarter has. These systems of measurements, or units, are vital to communicating our measurements to the world. Without them, we just have a bunch of useless numbers. There are two main types of units in the world: the ones you're familiar with, known as the imperial system, and the ones the rest of the world commonly uses, which you know as the metric system. For years, the United States, Liberia, and Myanmar have been the only 3 countries in the world who've chosen to use the imperial system over the metric system. As you know, in the imperial system, we measure length in inches, feet, yards, or miles, mass in ounces, pounds, or tons, and volume in fluid ounces, cups, quarts, or gallons. If you own a car, you might have even heard of our unit for pressure, pounds per square inch, or PSI. The metric system was created by the French, and it's actually called the Système International des Unités, or in English, the International System of Units, abbreviated SI. Everyone else in the world uses this system for units because it's super easy and it just makes sense. For length, the unit is meters, with its various prefixes giving us millimeters or centimeters or kilometers. For mass, the unit is grams, giving us milligrams or kilograms as well. For volume, we have the liter, which gives us milliliters or kiloliters. And for pressure, we use the Pascal, giving us millipascals, as well as the more common kilopascals. You may have noticed the kilopascal abbreviated kPa on your tire gauge. So I mentioned those prefixes. What do they mean? Well, they're simply multipliers of the base unit. For instance, a kilo is 1,000 base units. So if I have a kilogram, I have 1,000 grams. A milli is 1,000th of a base unit. So a milligram is 1,000th, or 0.001 grams. The SI system is easy because to convert between SI units, you just have to move the decimal over a certain number of places. To help you in the long run, I would like you to memorize the prefixes, symbols, and numerical values on this chart. The best way to do this is to come up with some phrase to memorize the order of the prefixes, and then memorize the pattern in the numerical value column. For the most part, as you move from top to bottom, each unit decreases by a factor of 1,000. Deci and centi are the only exceptions to this rule, moving a factor of 10 and a factor of 100 respectively. For the prefixes, I came up with the phrase, "Great Mama Cain did cite my ultimate novel piece." Does it make sense? No. Do I remember it over 12 years since I made it up? Somehow, yes. The abbreviation for micro is the Greek letter mu, which kind of looks like a U with a funny tail. That's where I got the word ultimate from. A base unit is a unit that is based on some actual object or event in the physical world. The base unit for time is the second, which is based on the frequency of radiation given off by a cesium-133 atom. The base unit for length is meters, which used to be considered as 1/10,000,000th of the distance from the North Pole to the equator, running through Paris in the 1800s. Later in the 1960s, it was redefined as 1,650,763.73 wavelengths of the emission line of krypton. With advances in technology, the definition continued to change and is now defined as the distance that light travels in a vacuum in 1/299,792,488ths of a second. The base unit for mass is the kilogram, which is based on a cylinder made out of platinum and iridium that's stored in France. In fact, that cylinder is stored under 3 different bell jars and multiple vacuums with no oxygen around it so that it doesn't oxidize. This is the only unit that comes with a prefix already attached. When we do conversions, we'll consider the gram to be the base unit on our chart. Finally, the SI unit for temperature is Kelvin. 0 on the Kelvin scale corresponds to the theoretical temperature at which all motion and matter stops. Let's talk a little bit more about temperature. There are three different temperature scales that are widely used: Fahrenheit, Celsius, and Kelvin. The Fahrenheit scale is used in the US and is really good for talking about the temperatures that we often experience in daily life, like the weather. As you probably know, on the Fahrenheit scale, water freezes at 32 degrees and boils at 212 degrees. The Celsius scale, which is used everywhere else, sets the freezing temperature of water at 0 and the boiling temperature at 100 degrees. Finally, for Kelvin, which we often use in science, especially when dealing with gas laws, water freezes at 273.15 degrees and boils at 373.15 degrees. A 1 degree difference in the Celsius scale is the same as that on the Kelvin scale. The Kelvin scale just sets the number significantly higher. If you were asked to convert between these three scales, here are the four equations you could use. To convert from Celsius to Fahrenheit, you multiply the Celsius temperature by 9/5 and then add 32. To go the other direction, from Fahrenheit to Celsius, you subtract 32 from the Fahrenheit temperature and then multiply that answer by 5/9. Kelvin and Celsius conversions are significantly easier. To convert from Celsius to Kelvin, you just add 273.15. To go from Kelvin to Celsius, you subtract 273.15. If you want to go from Fahrenheit to Kelvin or vice versa, you'll have to convert to Celsius first and then convert to the desired temperature scale. There are other very important units in the SI system that are not based on physical events or objects, but are created from a combination of base units. These are known as derived units. The SI unit for volume, the cubic meter, is a derived unit. It's the same as the volume of a cube with all sides equal to 1 meter. Imagine a meter stick, and then imagine the size of that cube. It would be pretty big. Most things that we measure the volume of in chemistry don't have volumes nearly that large, so we tend to work in the area of the cubic decimeter. A decimeter is 1/10 of a meter, or 10 centimeters, or just a little under 4 inches. This is a much more usable volume that we call the liter. We can use the liter the same as we do base units on our conversion chart. Another one that you may have heard of is the cubic centimeter. This is often heard in medical dramas when a doctor requests 10 cc's of some drug, stat. A cc is a cubic centimeter and is also defined as a milliliter. You might have seen milliliters before on labels to your bottles of water or pop. A 16.9 fluid ounce bottle is often also labeled as 500 milliliters. Density, which we'll talk about in the next lesson, is often expressed in the derived unit of grams per cubic centimeter, or grams per milliliter. Speed also has a derived unit, measured in meters per second. So, why metric instead of imperial? Well, since you're used to it, you can probably convert some measurements in your head, like how many inches are in so many feet. This may seem easy, but it's similar to the English language, in that the arbitrary rules that someone made up for this makes very little sense. There's 12 inches in 1 foot, 3 feet in 1 yard, 5,280 feet in 1 mile. How can you be expected to memorize all of those weird numbers? Even better is volume. 8 ounces to a cup, 2 cups to a pint, 2 pints to a quart, 4 quarts to a gallon. It's completely inconsistent. With the metric system, all you do is move the decimal point a certain number of places. For instance, to get from liters to milliliters, I move the decimal to the right 3 places, or multiply by 1,000. Here's an expanded chart of the metric prefixes. The darker green row is where we put our basic unit, usually for us the meter, the liter, or the gram. All of the light rows are those that only move 3 decimal places at a time. The 2 light yellow rows are the 2 that don't move 3 decimal places, but only 2 or 1. A quick and easy way to convert from one metric unit to another is to use the multiplier column. For instance, if I had 85 micrograms and wanted to know how many grams that was, I'd say it's 85 times 10 to the negative 6 grams. That means you move the decimal, after 85, 6 places to the left. That would give us 0.000085 grams. Alternatively, if we had, say, 73 megagrams, that's the same as 73 times 10 to the 6, or 73, but move the decimal 6 places to the right. That gives us 73 million grams. The conversion factor column is my personal favorite, as it can be very useful when we're doing multi-step conversions. We can use the information in that column and split it right into our calculations. These conversion factors tell us the equivalent amount of 2 different units, and we can use them to convert from one unit to the other. For example, we know that 12 inches equals 1 foot. What happens if we use a little bit of algebra and get all of our units on one side? We could do this by dividing 12 inches on either side. What does that leave us with on the left? 1. 12 inches divided by 12 inches equals 1. This tells us that 1 is equal to 1 foot over 12 inches. 1 foot over 12 inches doesn't really sound like 1. It sounds weird. But it is equal to 1. We just saw the mathematical reason for that. That's why I like to call conversion factors fancy forms of 1. Alternatively, we could have just as easily divided by 1 foot on either side and got that 12 inches over 1 foot equals 1 as well. So you know that we can multiply anything by 1 and it doesn't change its value. Well, we can multiply a measurement by a fancy form of 1, like 12 inches over 1 foot, and it doesn't change the value of that measurement. All it changes is the units that we're expressing that measurement in. For example, what if I knew that our classroom tables were 4.5 feet long? How many inches is that? In your head, you're probably thinking, well, since there's 12 inches in a foot, we just multiply 4.5 by 12 to get our answer. Here's how we can check for sure. If I write down my measurement first, the 4.5 feet, I know that I can multiply that by a fancy form of 1, and all it does is change how I'm expressing that length. It doesn't change that actual measurement. So, would I want to multiply that by 12 inches over 1 foot, or 1 foot over 12 inches? This is the part that many students struggle with the most, because fractions are hard sometimes. Really though, it's very simple. Whatever unit I'm starting with, feet in this instance, I want on the bottom of my fancy form of 1. Because being on the bottom means that I divide, and that means that unit cancels out. So to get from 4.5 feet to inches, I multiply by 12 inches over 1 foot. Feet cancels out, and I'm left with inches, the unit I was looking for. To get my answers, I multiply the numbers on top and divide by the numbers on bottom. So in this case, it'd be 4.5 times 12 divided by 1. Most of the time, you could just skip the ones because they don't actually change the number. So when I punch that in my calculator, I get that our tables are 54 inches long. We just did something called dimensional analysis. It's just a fancy term for converting our units by multiplying our measurement by a series of fancy forms of 1. To do this, start out by writing out the measurement and its unit that you're given. Write a big X and a fraction bar. Fill in the fancy form of 1 on the fraction bar, making sure that you put your unit from your original measurement on the bottom of that fraction. If that doesn't get you quite to the unit that you need, write another X, another fraction bar, and multiply by another fancy form of 1. Keep doing that, making sure that you're canceling out units as you go, and eventually you'll end up with the unit you're looking for on top. Each fancy form of 1 that you multiply should have a denominator with the same units as what was on top in the previous step. When you've gotten to the point where all units cancel except the ones you're looking for, multiply all the top numbers together, then divide your answer by each of the numbers on the bottom. Double check to make sure that your units canceled correctly, and then report your answer with the correct unit. We'll do some examples of this in class. You already know a lot of imperial conversions, and the SI chart is pretty easy to follow to convert between metric units, but converting between imperial and SI units is probably something new to you. We use the same process as before, but we'll have to use one of these weird fancy forms of 1 that are probably new. You don't have to memorize these at all. You'll always have your chart that's glued into your notebook with this information. These conversion factors work exactly the same as any other conversion factor. For instance, if I wanted to convert from pounds to grams, I'd put the conversion factor of 1 pound equals 454 grams into a fancy form of 1 with the pound on bottom and the 454 grams on top. We'll do some examples of these in class as well. So we've talked about measurements, their units, and how to convert between them. But another important aspect of reporting our results is making sure others know how good our results are. We do this by expressing the accuracy and precision of our results. Accuracy is how close our answers are to the correct or true answer. We express this using error or percent error. Precision refers to how close your measurements are to one another. For instance, if you took 5 measurements on the same object, you might get slightly different results each time, depending on how good you are at measuring. The closer the measurements are to each other, the more precise they are. The method of reporting your answer to the correct number of significant figures helps express how precise the measuring device itself is, while expressing the standard deviation helps us show how precise the person doing the measuring can be. The classic illustration for precision and accuracy are dartboards. Hitting the bullseye is like hitting the right answer. You're really accurate if you hit the bullseye or near the bullseye. Regardless of where you hit, if you hit the same spot on the board consistently, you've got high precision. So you're accurate if you get close to the right answer, and you're precise if you get the same answer over and over. For percent error, the calculation is very easy. You simply take the value that you got minus the theoretical or true value, ignoring any negatives, and divide by the theoretical value, and then multiply by 100. Standard deviation looks a little bit more complicated, but it's almost as easy. To compare your individual measurements to see how far apart they are from each other, we use this equation. The closer your standard deviation is to 0, the more precise your measurements are. In this equation, the x1, x2, x3, etc. are the individual measurements that you take. The x with the bar over the top of it, known as x bar, is the average of all of your values. N is the number of measurements that you took. You'd report your answer as the average plus or minus the standard deviation. To report the precision of your actual instrument, we use significant figures. Significant figures are just a common practice way for scientists to report their measurements, so that any scientist can look at the number given and know to what decimal place the instrument is actually able to measure. We call this the degree of uncertainty. When we measure what we're able to read and then guesstimate one digit past that. The last digit is uncertain, but we assume that it's within plus or minus 1 of that digit. For example, this graduated cylinder here on the left only reads milliliters by the whole number. We can only for certain say that it's between 4 and 5 milliliters. It'd be incorrect to simply report it as 4 milliliters. We have to guess one digit past that. To me, it looks to be more than halfway between 4 and 5, maybe even 3/4 of the way to 5. So I'm going to report my answer here to be 4.7 milliliters. When someone reads that, they should be able to tell that my device measures in whole numbers, 1, 2, 3, 4, and that tenths place was my best guesstimate of where the measurement lies. Since I reported it as 4.7, anyone should expect the measurement to be anywhere between 4.6 and 4.8, so plus or minus 0.1 in this case. I take that liquid out, I pour it into this other, more precise graduated cylinder that reads all the way to the tenths place. Now, when I report my measurement, I have to measure one place past that, all the way to the hundredths place. If I look closely at it, I can tell that it's somewhere between 4.6 and 4.7 milliliters. And that's if I'm measuring from the bottom of the meniscus, like I should be. So I'm going to report this as 4.65 milliliters. Anyone can read that and know that my graduated cylinder reads all the way to the tenths place, and the actual volume could be anywhere between 4.64 and 4.66 milliliters. When you're looking at a reported measurement, sometimes it's difficult to know where the degree of uncertainty lies in the measurement, particularly when zeros are involved. Here are 5 easy rules to help decide which digits in a number are considered significant. Easy peasy rule number 1, if the scientist bothered to write down a number that wasn't 0, it's significant. Rule number 2, any zeros that come before the very first digit that's not 0 are just placeholders and they're not significant. Rule number 3, any zero that's trapped between two not 0 numbers is significant. All 3 of those rules are fairly easy ones. The 2 tricky ones are when we have zeros to the right of the last number that's not 0. If those zeros are to the right of a decimal, they are significant, because they're telling us to what decimal place our measuring device was able to measure to. If they're part of a whole number, and there's no decimal to be seen, they're assumed to be not significant. Although this is kind of ambiguous, and that's where scientific notation comes in handy, which we'll see in a few. If the scientist slaps a decimal at the end of the whole number, they're doing that to tell you that all of those zeros there are significant. The short version for all these rules is that you need to look at the number and find the first non-zero digit from the left. Then you can always assume that zeros before it are not significant. And usually the zeros after it are significant, especially if they're after a decimal. For really big numbers or really small numbers, it's nice to look at them in scientific notation. The nice thing about scientific notation is that when we have a number like 1,100,000 with 5 ambiguous trailing zeros, it's hard for us to tell where the guessed digit was unless we use scientific notation. It could be that a device measured to the hundredths place. How could we possibly report that? We can't just slap a decimal after that digit because it doesn't belong there and it would change the meaning of our number. And it would be cumbersome to underline that 0 to signify that the uncertainty lies there. Scientific notation is the answer to all of our problems here. You've been doing scientific notation since like 7th grade, so I'm not going to explain all the rules here. They're here to copy down and to look at should you need them. The important thing I want you to understand here is that when we're looking at a measurement in scientific notation, no matter how many zeros are in it, you can assume that all of the digits written before the times 10 to the part are significant. Now that we know the rules for figuring out which digits are significant or not, we can talk about what to do when we have to calculate measurements. When you multiply a series of conversion factors or add a series of measurements together, it's very easy for you to end up with a lot of numbers after the decimal, especially if you're punching it into a calculator. If we were to report our answer as the calculator tells us, other scientists would assume that our instruments were able to measure down to that decimal place. The general rule is that we're not allowed to report an answer that has more precision than the least precise measuring tool gives us. For example, if I had a series of different rulers, some that measured in only centimeters, some that measured clear down to the nanometer, and I used each one to stack up against each other, measuring the length of a table, I would not want to report that answer to the nanometer, because some of my rulers couldn't even measure that precisely. So the 2 rules are very simple. For adding or subtracting, you look at whichever measurement has the least amount of decimal places, and then round your final calculator answer to the same number of decimal places. When we multiply or divide, we look to the measurement with the least amount of significant figures for guidance. Count the same number of digits in your final calculator answer, starting at the left, and when you've hit the same number of sig figs, cut your answer off there and round the rest of it. In either case, you should ignore any counted numbers or conversion factors and only look at the measured numbers to determine how to report your answer. Well, that's all for today, folks. I know that was a lot to take in with only a few examples, but the point of this video is to give you the rules so we can be ready to go through the examples together in class. As always, if you have any questions, ask.